which actually makes a video. The intermediate value theorem, again, the big caveat is that you have to have a continuous function. You've got a continuous function on a closed interval from a to b, and let's say that w is some y value between those endpoints of f of a and f of b. Then we're guaranteed that there is some c, which is an element on a and b, such that f of c equals w. Let's see this in action. This is the problem that I wanted us to talk about. We're going to use this idea. Let's use the intermediate value theorem to show that the function listed below has a 0 in that interval. Well, the interval that you see is -3 and -2. So help me out here. If we get f of -3, well, we could very quickly, I hope, just say here's 3. We type in -3, and we're going to raise that up to the third power. We'd say -10 times -3. And then we could say +9. And once we plug that all in, of course we could work that out by hand. We'd get -42, right? Well, what else do we want to do? We should plug in f of -2. Find those two y values at the endpoints. Now, f of -2, take out your calculator. Sometimes kids are like, oh my gosh, if only I could just recall what I just typed in and just go over the -3 and replace it with a 2. Do you know that you can do that? Have you guys ever learned that? No. Okay. Second enter. Hit second enter. And beautifully, what you just typed in comes back again. Right? Pretty cool. So I'm going to bring my left arrow over here and say, you know what? Instead of a -3, my goodness, I'd really like to make that a -2. Plug in that -2 over here, and look at that, you get a 5. Now, guys, I guess real quickly, I just want to make a quick sketch. You don't have to make a quick sketch, but hopefully just making it crystal clear. At f of -3, I'm down here with a y value of -42. At f of -2, I'm up here with a y value of 5. Now, when you're asked to find if you have a 0 of a function, that means that the y value would equal, take a guess, 0. That's why we call them zeros of the function, right? We want the y value to equal 0. So I guess what I'm really pointing at, guys, is assuming that our function is continuous because every polynomial is continuous, right? Every polynomial is continuous. If that's the case, are you guaranteed that you're going to hit a y value of 0 somewhere? Just if I gave you that picture? I think common sense would say, of course. So look, this is what we're going to do. It's almost like a little proof, not like the proof that you wrote last year in AGT with 2 columns and so forth. But this is what you're going to do. You're going to say f is a polynomial and is continuous everywhere. Or you could say continuous on the closed interval from -3 to -2. Say one of those two things. Either it's continuous everywhere or it's continuous on the closed interval. It's true for both. And then we could say, well, in addition to that, I'm going to say 0 is between f of -3 and f of -2. F of -2 was the positive 5. F of -3, we saw by working that out, was -42. In other words, 0 is between those two extreme values. Guess what we're going to say now? By the intermediate value theorem, by the IVT, there exists a C value on that, well, actually on the open interval from -3 to -2. I don't know what that C value is. I'm going to write it in right here on my picture. You see that? That x-intercept I'm calling my C value right here. There has to be some x value such that f of C equals 0. I don't know what the x value is. We could use a calculator tool to do that. But I guess what I'm getting at is this in a bigger sense. If between those two y values you change from negative to positive, somewhere you're guaranteed you must hit 0. And that means you are guaranteed you must have an x-intercept somewhere within those x boundaries. Are we doing okay with that? Okay, so that, by the way, is just what we have for the intermediate value theorem. For tonight's homework, and I'll remind you about that, you might remember I was going to give you 73 and 75 from page 232. We will put that onto our new assignment tonight just to get you some practice. And on our quiz, we will have one intermediate value theorem question. Well, that being said, let's jump into the notes for section 4.3. Your notes are nice and fixed up. My notes, sad to say, are an electronic version of the older version. But we mentioned this yesterday. We said, hey, let's talk about the complex numbers. Let's review what we've got for complex numbers. If you have two real values for a and b, if a comma b is a real number, a plus bi is a complex number, where I represents the imaginary number, the square root of -1. What do these complex numbers look like? Well, 3 plus 2i might be one example. 7 minus 4i could be another example. And we could definitely continue on. But these are not real numbers. They're simply complex. So at this point, I guess what I'd like to point out is this theorem says every polynomial with real coefficients and degree n can be factored into n distinct linear factors, and it could very well be that that these roots here could in fact be complex. What I've highlighted here, though, and I'm going to put a little star right next to it, this can be so very, very, very helpful. Given that you have a polynomial f of x, if a plus bi is a 0 of f of x, then a minus bi is also a 0 of f of x. Now, I hope if you thought about that long enough, it would make sense why that must be true. And I'm trying to skim this. I'm actually making this video here, so I'm trying to streamline the lesson a bit. This comes from the quadratic formula, right? And we even sang that song yesterday, right? And you could say, well, it's x equals opposite b plus or minus the square root of b squared minus 4ac all over 2 times a. Guys, it's the plus minus that will generate those conjugates, the a plus bi and the a minus bi. So you'll always get those complex solutions in pairs of conjugates. So that being said, I would like to point out that the author suggests doing things in a really brutal, tough way to do some of these problems. I'd like to give you a gem of forgotten math. Math that is really not taught very much anymore. I really feel it's a tragedy. I feel it's very sad it's not taught anymore. I'd like to show this to you. I think you're going to greatly appreciate it. Given ax squared plus bx plus c equals 0, given ax squared plus bx plus c is equal to 0, you can know and R1 and R2 are roots or solutions to that equation. I don't know if you've ever seen this before. R1 plus R2. Does anybody know? I wouldn't be surprised if kids were silent because it's really not taught. R1 plus R2, amazingly, add up your two roots, you'll get opposite B over A every single time. If you want, I'll prove that to you later. It might seem a little hard to believe at first. Furthermore, if you multiply your two roots together, guess what you're always going to get? C over A. C over A. So the addition of the two roots will always be the opposite of B over A. Sometimes students will understandably say, well, what do you mean B and A and so forth? Well, my goodness, right now I hope that you know that the B that I'm talking about is in the quadratic equation up here, and here's your A. And the C is up there as well. So, tell you what, if we know this, we can do example 1 way quicker than what the author is suggesting. You see, the author is saying, could you name a polynomial of degree 4 for number 1, whose coefficients are real numbers of 2, 2, and negative 3 plus I. Now, don't copy this down. This is what the author is suggesting that you would do. He's saying, first of all, the 2 here, guess what a factor would look like? X, help me out, what do you think? Minus 2, and then kids would say, here's another x minus 2, and then the author suggests, horror upon horror, that we also FOIL this thing out. Ooh, really not looking like too much fun. Do you see what I'm getting at? And then he's saying, and then from there, let's deal with the conjugate as well. We're not going to do that. Ooh, what a relief. But all the same, we'll have to talk about this in just a moment. Here's a 2, here's a 2. Negative 3 plus I. I'll call this one of the roots that we are given. What's another root that they didn't write down? We should know that's coming. What do you think? Negative 3 minus I, the conjugate. Right? If you have A plus BI, A minus BI must also be a root. So as soon as they give you one complex root, you've got a second one thrown in for free. Now, the author is suggesting that we painstakingly multiply all of that out, and that becomes quite intimidating. I'd like to suggest an easier way. Let's take your R1 times R2 and call it C over A. How about our R1 is just negative 3 plus I, and let's multiply these things together. Let's do that. Now, by the way, we've got conjugates at play here, right? We've got some conjugates. Hopefully you remember how to multiply conjugates together. I'm going to write it on the board. Big X plus Y, big X minus Y conjugates. What do they multiply into? X squared minus Y squared. Now, could you FOIL it all out? Of course you could. What's negative 3 squared going to get you, though? 9 minus I squared. What is I squared? You guys remember what that is? Negative 1. If you forgot that, please recall it. C over A is really going to be 9 minus negative 1. 9 minus negative 1 turns into 10. C over A is really equal to 10. You can say, okay, where are we going with this? Well, there's another part. What's R1 plus R2 going to equal? Opposite B over A. Here's negative 3 plus I plus negative 3 minus I. What does that work out to, guys? Look at the I and the negative I canceling. We get negative 6. We're just adding them.